Welcome everyone to another episode of the Common Lisp Study Group. I'm your host Ram Vedam with Atlanta Functional Programming. Today we're going to be continuing our discussion of the FSet library, a library that contains functional, set theoretic collections, as well as some iteration constructs around those collections. Last time when we discussed this, we've discussed kind of the 3 of the 4 major data structures that this library provides. Now, today we're going to be continuing our discussion with the final data structure that it provides, some of the iteration constructs, and if time permits, I will introduce you to a newer version of another version of a data structures library, kind of in the guise of FSet, but more in line with how Common Lisp attempts to implement various generic algorithms for various data structures. But time permitting, that topic may not be able to be covered in this episode, but we'll certainly cover it in another one. So, like I mentioned, we covered very briefly as a review sets, maps, and seeks. Very quickly, for those of you who were not with us last time, sets are basically just your standard mathematical set. So it's a group of unique members. You have your standard ability to create an empty set using FSet empty set. You have the ability to create predefined sets using FSet :set, and you can add members to sets using the with keyword. Now, one thing that I've mentioned before, and I'm just going to reiterate here, all of the FSet collections are immutable by default. So when you use these adding and removing methods, adding a member is with, removing a member is less, just the same thing as in most of the collections that are in this library. You end up returning a new version of the set. The old set is not modified. There are a bunch of standard set member functions to actually go manipulate sets, things like, union, intersection, set difference. We've discovered, we reviewed last time, that set actually provides 2 different versions of set difference. The first version only gives you the one direction of the differences, meaning it will give you the difference of the first argument minus the second argument, returning all the members that are in the first set that are not in the second, whereas set difference 2 gives you the both directions has multiple return values. The first return value is a minus b, the second return value is b minus a. One feature that was limiting in the set library that I covered here that we were able to quickly introduce is proper subsets, because subsets inside the FSet library were just, they were sets that could be the whole set itself. And sometimes you may want just strictly a proper subset of the set. So one way of writing that is literally just writing a set difference and making sure that it is not empty. So we went ahead and did that, and wrote ourselves a little function to actually go and handle that. Of course, it can handle disjoint sets. Additionally, we covered maps as well, and they have a similar API as sets. One thing to note about this, again, that we covered last time, was sets, maps, and seeks may have similar functions, but they have different function names. They are not generic functions. These are not hooking up into the generic function infrastructure that's available through CLOS. So if you're dealing with set, intersection, union, and so forth, you'll be using set. You'll add set dash intersection, set dash union, and so forth. Maps are similar, as you can see here in this example on line 67. Instead of calling union, we're calling map-union. Also, we covered some special characteristics of seeks. Now, seeks are like sequences that are in common Lisp. The difference being that they're immutable by default. There are some bits and pieces of functionality that you can you get with using FSet that you won't get with normal sequences. For example, when you're modifying an index to a seek data structure in FSet with the with keyword, whether you're adding or you're removing something, there are some distinctions about the first argument and the second argument. The first argument is usually the index into which the seek data structure that you're trying to modify, which will effectively do an update. If you are adding at the end of a given collection, so in our example here, seek example, we have only 3 items. If you use an index that clearly doesn't have a value, which means you're adding at the end of the collection, you are essentially modifying and creating a new version of that seek data structure, in which case you will end up just adding like a con. It will essentially do like a cons at the end of that structure, although internally it will do something slightly different for efficiency purposes. Additionally, FSet provides the ability for you to change the default value that can be inserted through its API, so that if you're trying to have filler in between values that you're trying to add and updates and so forth, the default is usually nil. Instead, you can use with default to actually go and change the default, which is what we did here. I encourage you folks who are just joining us and are not familiar with the majority of this. I tried to cover the majority of the key points from last time. Please go ahead and refer to our previous episode for more information. So we're going to be talking about bags. What is a bag? Bag is really FSet's term for a multiset. Now, for those of you who aren't familiar with multisets, multisets are a special type of set data structure which allows duplicates, and it creates essentially a non-negative number called the multiplicity factor, which represents the number of occurrence a particular member is in the multiset itself. So it will end up when you're returning this set, it'll end up keeping an associative list where each occurrence has this multiplicity factor associated with it, representing how many times it actually was added to the set. To show this, we're going to go ahead and create our simple example map. Sorry, example bag with our FSet empty bag. And this is just creating, dang it. Do this again. All right. If we go ahead and print this guy, you'll see that this is the reader macro that's created by FSet to represent a bag. It's hash percent instead of hash brace percent instead of hash base brackets, if I remember correctly, for our. Go ahead and do empty set. You'll end up seeing. I renamed that. Go ahead and rename this guy. This is for our set reader macros and our maps. All right. And obviously, example seek. There we go, which is represented like a vector. I'm only showing these just so that you get a sense of when you're playing around with the FSet, especially using the FSet user package, you understand the output that's coming out in there. Although internally they may be objects of and they are objects with an object hierarchy. That's an implementation detail that really you shouldn't have to care about when you're leveraging these data structures. Okay, so we have a question just from a review from last time. If the question goes, if I have a sequence with 4 elements and I give it a larger index, say 10, will it extend the sequence using the defaults? Yes, that is exactly what happens. You end up, it takes whatever index you provided and whatever the size number is and increases the capacity in a new copy of the data structure. And then it uses the default value to fill in those values. That's where that filler comes in. So let's talk about bags. So now that we have an empty bag, which is a multi-set, let's go ahead and add some stuff to this bag, right? And I'm going to go ahead and do 2 examples of this. One with the empty bag version, obviously with the with keyword, just so that we could see what's happening in real time, and then what happens if we end up using the actual bag constructor to construct a bag, because it'll show you similarly what would end up happening. So if we use this bag here that we just created, and we just end up using, and I'll go ahead and copy this into the script after we're done. We use the with keyword on the empty bag, and we say, okay, let's add 1, 2, and then 1, right? Actually, you know what? I take that back. Let's say that we have 1, right? Because I think we can only add, 1 and 2, right? Because what we did here is we actually added 1 twice, right? So let's go and look at that function signature again. Remember, in FSet, the with keyword takes in 2 values. The first value is usually dependent upon which data structure you're using. What the first value is interpreted differently. So in the case of bags, the first argument after the collection, it represents the value you're adding to the structure. And the second time you add, the second value that you added is actually going to be the number of times it's added automatically, all right? And that represents the factor. So if I do with 1, 2 here again, it'll create this structure here that has 1 and 2 with the multi-value. Let's go ahead and set this guy in a and let's add to this guy. And again, this is usually something that you don't really want to do a lot of times, just because you're dealing with immutable data structures here. But I'm just doing here for the sake of example. Let's say that you want to add to test bag. Okay, another 2, right? You see automatically that second value, that multiplicity, is going to be increased. So if we end up adding, say 2 here, you'll see that the data structure that's being written, initially when it adds it, it doesn't actually create the multiplicity factor. It is set to 1. So this is going to be a little jarring for folks who are looking at, who are typically used to using data structures that have, a uniform representation across every member that's inside of the data structure. Well, the multiplicity factor is just nothing more than a, think of it like a compressed version of the data structure and what it actually represents. So it's saying that, we're using like runtime length encoding, where this is saying that one is in the set 4 times, followed by 2, and then followed by whatever additional members. So we can see here, just to show you that as we keep adding to this structure, the multiplicity factor goes up. One of the nice things about this now is you can easily look at this, at least at the REPL, or if you're introspecting the data structure, and quickly figure out if you have, like, say, if you're using the multiset as a way of detecting, if a particular item has been, added to your, say, like, let's say you're using it like a shopping cart. You can use this multiset to actually go and see how many times you add a particular item. The rest of the API is pretty straightforward. If we wanted to create this from the, just from the get-go, we can go ahead and do that. We can use our good old FSet bag constructor, and then we can, keep on adding our values that we want to add in. Notice that I'm putting this in any order. This doesn't have to be in any particular order. It will go ahead and get compressed when it gets added to the set. So when we do this, we get a compressed version of it. Also notice that, just like every other our set data structure, it does sort based on the value that's inside the set. So it will end up giving you this structure where the first value is going to be a set, and it clearly recognizes when a particular value is inserted multiple times, as you can see here with the 1 being indicated as being inserted into the multi-set multiple times. The rest of the values, API functions are pretty much the same as our previous data structures. So we have union, set, intersection. So if we end up, creating another, let's go ahead and call this guy bag 1. And let's create a similar bag 2 with, some duplicates, but we have some also new values, and so forth. So one of the nice things about this now is you can actually go ahead and say FSet union bag 1, bag 2. Please notice I am not using bag I didn't actually put bag associated with this. That's because bag actually uses some of the same functions that union and intersection does for sets, because it's a similar semantics, although there are multiple members in this case. And this is actually indicated in the function signature. If we actually go and look at the function signature, you can see that it says set or bag 1, set or bag 2, and then we can provide different tests inside of the bag. And bags can hold structures and data structures. So if you're especially using this for structure holding and object holding, you can certainly use those two things to, add particular additional tests that you can certainly do. Obviously, in this case, although I'm asking for the defaults right now, I could add, let's say I only want to have the union of all the odd numbers and stuff like that. I can certainly do that. We're not going to spend too much time on playing around with these key values, but I'm just going to mention that they are there. So if we go ahead and do union, you can see, whoops, I forgot to actually recompile this guy. Boom, boom. Now we can do it. There we go. You can see that we have union, we have intersection, just like before with sets. I don't believe we have difference. I don't believe there is a set difference. Let's see. Can we do set difference on this guy? I don't believe so. Yeah, no, this is strictly for sets. There is bag difference. That's what I was looking for. Okay. So one thing to note about bag difference, so in this case it is still following the same semantics as set differences, but it doesn't have a bag difference too. So if you go and look at, this might change in a newer version of FSet, like he might add it to the API if it becomes inconvenient, or it'll make the API more uniform. You can clearly see that bag difference is the only one that's available. Now, you could certainly mimic what he had by doing this. Bag 1, bag 2, then values, FSet, bag difference, bag 2, and bag difference, bag 2, and bag 1. And this gives you the same semantics as set. Oops. Let me do this. Keep forgetting that when I use it in a buffer, it'll actually return the multiple return values, but it won't do it inside the code, like inside of a file. It's a little weird. So if you do this, it compiles and loads. I mean, there's no warnings, but it doesn't actually run it. Whereas if you actually throw it into the REPL, it will go ahead and interpret the value. So you can see that this is exactly what we had before with set difference too. And if you wanted to then, for example, do what we had before, we can add, go ahead and do this. This way, we can use what we had before, which is multiple value bind. bag 1 minus bag 2 is equal to bag 2 minus bag 1 is better. All right. Go ahead and clear that. All right. In addition to these core common, actually, before I mention the newer functions for bags, there's one more thing I need to show you, which is I've shown you width, but I should also show you obviously less. So if we do FSet width, bag 1, 6 here, and then this. So if we have width, we can add something, we can remove something. So in addition to this uniform API that's provided for adding, removing, doing union, doing sets, doing doing intersection, difference, being able to add different sets into old sets and so forth. There's two additional functions that I should mention to you, which is actually three functions. And that is bag sum, bag product, and size. Okay, let's start with size, just because size is something that will be very, very commonly used. So when we talk about size in multi-sets, we are talking about the number of elements inside of the set, but we are not talking about the number of unique elements inside of the multi-set. So to figure out how many unique elements that you would have to that are inside of the bag, you have to use set size. Whereas if you want to know the number of total elements inside of the multi-set, you want to use size. Let's take, for example, bag 1. We already know that bag 1 has, you can see this here, 2 elements for 1, and 1 element for each of the other elements inside the set. So that's 0, 2, 3, 4, and 5. Right, so that means we have a total of 7 elements in there, but 6 actual unique elements inside of this set, right? If we want to know the number of elements inside of the bag, we can just go ahead and do size. All right, this will go straight up, do an add of all the multiplicity factors, and then just reduce them and give you a value. If you wanted to know what the number of actual unique elements, you'd want to run set size, right? This is actually looking at the key value terms, and it's looking at specifically the values in it and running a count against the number of values that are inside of a multi-set. This subtle difference is very important too when you're dealing with bags. If you're asking for uniqueness that changes what you're dealing with inside of the multi-set. When you're asking for just straight up, statistics on your set, what is it? You can use size for your analysis. So there's two other ones I'm going to show you, and that is bag sum and bag product. And I think the best way to actually show you bag sum and bag product is to straight up take our two bags that we have here, bag 1 and bag 2, and just use it. So if we call bag sum, okay, on bag 1 and bag 2, it's going to give you essentially kind of like a union of all the values in it into a single structure. And we can see this if we do union bag 1, bag 2. All right. So you can see here what it did is it actually combined bag 1 and bag 2 into a single larger. So there's a subtle difference here. In bag 1 and in the bag sum, it's actually doing a proper union of the two sets and two multi-sets and giving you a full set. Whereas if you use set union, it's giving you a actual set union of unique elements, and the usually the one on the right is going to go with the larger multiplicity factor. That's one difference that you need to be aware of with bags. Multi-sets in general, APIs behave somewhat similarly in other languages. Let's talk about bag product now. And again, I'm going to go ahead and let me clear this REPL. And actually, let me first do something here, which is grab this guy and grab this. Oops. All right. And let's do this. I'm just going ahead and giving you guys these notes too as well, so that's why at the end, for folks who are using this, you can use this as a quick cheat sheet to know the difference. We'll give you proper union between the two sets, taking the left-hand side of the unique elements first if both are available. Actually, you may as well try this one. What is the difference between this? So if this guy is that, what is this guy? Oh, sorry. I'm looking at this one. So let me just go ahead and clear this guy here. Okay. Taking the side with the unique element with the larger multiplicity factor. The larger multiplicity factor first. Sum will give you sum up all multiplicity factors for both elements, or element in both bags before adding into the resulting bag. All right. Let's talk about bag product. So again, we have our two bags. I'm just going to go ahead and spit them out here for reference. Bag 1, bag 2. Right? And if we print the bag product of bag 1 to bag 2, and again, this is same arguments. You'll get essentially the intersection. But again, it's the same thing with if we did intersection here. And this is, I don't believe this, I think this is commutative too. It's going to give you the same results. So, but this is the equivalent to what we saw with union, but with set intersection. So if you do set intersection on bag 1, bag 2, you get 3, 4, and you'll get similarly the same thing here too as well, 3, 4. All right. So bag product is to intersection, has bag sum is to set to regular union, but there are subtle differences in the union case versus the intersection case. But the one thing to notice is in the case of bag product, it is dealing with the one with the larger multiplicity factor. Okay. So when you do an intersection, it's just going to take whatever the unique values are and return it into the multi-set. Whereas with bag product, it's taking the one that at least that has been added more times in the particular set and put that as part of the intersection group. Are there questions about bags and some of these things that I've just mentioned? Okay. So, so before we continue our discussion on just programming with these data structures, there is somewhat of a philosophical thing that was brought in FSet's documentation that I'm just going to go ahead and bring up here, and that is it's sort of reiterating what we were talking about last week about the purpose of a library like FSet and why it's there. And it goes back to, again, the fact that although the majority of the basic data structures inside Common Lisp itself are, because of the way they are constructed in their APIs, they're usually mutable data structures. And this includes even lists because cons, car, and kidder internally have certain optimizations done to them so that structure can be shared across multiple instances. With respect to lists and even vectors for that matter, just because they're both the majority of the APIs have been generalized to sequence types. Those actually are, for the most part, can be treated functionally. So a lot of sequence types can be treated functionally if you use the functional versions, and that is, and what I mean by functional versions, I usually mean the non-destructive versions of the operation. So instead of using nconc for concatenation, you'd use conc. If you're using you use push new instead of push and so forth to actually manipulate some of the data structures. This is particularly important when you're talking about and when you're using collections inside Common Lisp functionally. And there are quite a few operations that are available and for you to actually use those data structures in native and vanilla Common Lisp functionally. My point is, and the point of this library is that there are some data structures that aren't available as part of the core Common Lisp API. Some more uniformity between those data structures, and this goes back to just the fact that, at least with respect to the sequence APIs themselves, this is a bit of a pain point across all Common Lisp implementations. You can't actually write your own extensible sequence types. You only have at your disposal vector and string. Vector, string, and list. Obviously, there are and there have been extensions and proposals to actually go and create extensible sequence types, and there are actual reference implementations like SBCL, so user extensible sequences, and even libraries, one of which we'll be covering in future episodes, called trivial extensible sequences, for you to actually be able to leverage and use and actually create your own types. But they're not standard, and that's kind of somewhat of a inconvenience when you're trying to write functional code. So FSet attempts to actually resolve that by at least providing some of that uniformity inside of its API, as long as you stay within the data structures and its concepts. So when you're using the reason I bring this up is it's going into some stuff about how do we end up using our collection types and so forth. So we kind of iterated this last time a little bit, but this is just going to be a further understanding and a little bit of a deeper dive as to what's going on. The first thing to note before we begin is there's some things about this this library, at least for me, from my standpoint, that I'm not entirely sure what use case would be appropriate to use it. But I'm just going to go ahead and mention them here, and that is things like nesting of different collection types. So you can have sets of sets, map keyed by sequences, bags, and all these crazy combinations. When and where you would do that, and how much of a performance hit that's going to be if you end up creating those kind of complicated collections that are composed of each other. I don't have a good gauge of those performance numbers. I have to come up with a kind of real world example to give you somewhat more information on that. But I'm going to go ahead and mention that you could do those kinds of crazy things if you wanted to. For example, you can use this to implement things like parser generators. I've never written one using FSet, but I'm sure that if you go out and look out at other libraries, they probably have parser generators that implement the state table using this kind of a data structure. Okay, so let's talk about assignments a little bit more. So before, we've been using kind of vanilla, Common Lisp's approach to actually assigning to different sets. FSet itself provides several macros in dealing with some of this. I kind of showed a couple of these before, although it was in the FSet User API, and one of them is, and you will notice it's not available in here is iSetQ. If you're using FSet User, okay, and I'm going to go ahead and change to FSet User here just to kind of iterate this. FSet User actually provides iSetQ, which is a convenient thing to actually go ahead and in the REPL create new variables. So we can use this instead of using def parameter or even a let form to actually go and create new variables. So here, if I wanted to create a new set, I could go ahead and do that. And it'll create a set for us. iSetQ also has conveniences to what we saw before, whereas it's like you can set, a one set to another set, and you can do other operations too. But notice if we go ahead and add with S13, this still doesn't follow. This follows still the immutability property of all these data structures. It will return a new copy of those. So the user package allows you to manipulate some of the APIs that are available, but it doesn't necessarily mean that you're going to actually have some conveniences to be able to do some what I would call bad practices when you're dealing with immutable data structures. Does that make sense for folks? So you can certainly use iSetQ when you're in the FSet user package, but I encourage you, just so that you could get a feeling for the library when you're playing around with vanilla common Lisp, to try not using it and putting your manipulations in a top level package of your own, just so that you can easily switch between the REPL and your own code. This is just a practice that I've been kind of adopting, just mainly because some of these convenience APIs, while good for experimentations, aren't very good when you're trying to get something kind of well structured out and then moved into a file, even the scratch buffer, using FSet User. Now you could certainly do the following, although again I don't encourage this, just because I always get a little queasy when I see something like this, and that is you can use FSet User as part of your package, like this. And then and now we will have access to, iSetQ here. So 1, 2. Really, hold on. FSet User. Do I have to make a var? Variable s unbound. Interesting. Hold on 1 second. I thought I'd used this before this way. Undefined function. So it's still not available even if you do that. Oh, I just learned something today. I've used this with other user libraries. Well, I just learned something today, folks. You cannot actually use FSet User as part of that library. What? Just messed up my thing here. Give me a second. I have to restart my Lisp because I messed up my Lisp image by doing that. All right. Load with the FSet intro. Oh, right. And just do this. Sets. There we go. Okay, good. Let's go ahead and restart that guy. I wonder why it didn't grab that either. Set. Oh, dang it. There we go. Much better. All right. Sorry for that little diversion, folks. Back to what we were talking about. So, in addition to, and I'm going to go ahead and, just for continuing's sake, I'm just going to go ahead and mess this around with here so we can go through some of these examples that are I just straight up copied in my notes. And those are examples that are in the documentation if you guys want to take a look at it for more information. You can also see some of this inside the tutorials, a lot of which are available. But I'll go ahead and kind of illustrate some of this stuff just to go through them fairly quickly. One thing to note about some of these functions is something that I was mentioning earlier, but I didn't probably quite iterate correctly, which is when we're playing around with some of these inside of our REPL especially, you notice that a lot of these API functions that I'm actually demoing here have an F in front of them, which is something that is a bit jarring for folks who are used to using setF inside a common Lisp, which is that it's a generalized expander that's going to be mutating the particular structure in place. None of these functions that I have just shown you with less ISETQ, adjoinF, which deals with actually adding also two different sets together. None of them actually modify the existing set. So take, for example, if I make 4 here, and I do adjoin F, that's 1, that's 2, you'll see that it will, just connect them and add them straight into the set, but S1 and S2, adjoin F does actually mutate. This actually is something new. My understanding of adjoin F is that it does not mutate. Interesting. So adjoin F is the only one that actually mutates. ISETQ with less, a lot of these just do not actually go ahead and mutate their data structures. Does that mean that, we have an opportunity now to actually go ahead and do an use adjoin F to actually go and mutate? Adjoin F is not actually doing what you think it's doing. What it's doing is actually it's creating a new data structure, doing a set F behind the scenes. All right. So, excuse me for a minute. Sorry. In addition that's the first thing that I want to kind of mention. When you're playing around with some of these APIs, you might be thinking that you're doing mutation and stuff like that when you're dealing with these things, but these are functional collections. So always understand that you are creating a new collection. There's no shared structure at all. These are brand new collections, which means in some cases, if you're doing an iteration, you might be creating a lot of temporaries. Just be warned that is pretty typical. It's not going to necessarily be a big deal when you're making a lot of collections. It becomes a problem when those empty number collections forces a lot of garbage and forces a garbage collection to have to occur in order to provide you more memory. Just be warned. This is just pretty typical of all functional libraries. Now, with maps, there's something similar in terms of actual like modifying a map. You may think that you can modify a map, and technically you are modifying a map if you're actually adding, a value in there. But that's just what's actually happening behind the scenes. It's kind of what incf does. Incf, what it does is it does a set f internally after it does a straight up increment, which is a functional approach of actually having to deal with a particular value. So if you end up setting up a value, for example, say count of 0, and we use incf of count, doesn't actually do what you think it's doing. It's not doing a straight up increment. It's taking the temporary and then pushing it and overriding the temporary and garbage collecting the other one. So with maps, you have something similar. You have to, let's start with, kind of like creating a simple map. Let's call it simple map. This guy has an empty map with our default value is going to be 0, right? So that means when you are adding a new value, it automatically will get a default value if you don't provide anything of 0, right? So the key for any new key, the default value is 0. So with that, we can go ahead and use the @ sign, which is just lookup. It's a convenience macro, as you remember, and add values to simple map. You can see that right now it's not there, but if we do incf on looking up simple map, and we do simple map now, you can see that we didn't provide a value to x when we inserted it, but we were able to modify it and then in place using incf. So it's very similar. You can use it for other things. Adjoin f, as I mentioned, is another way of actually going, inserting stuff into your map structures and stuff like that in a set f kind of way. But remember, you are still just accessing that thing in memory, and it's throwing away the old value and adding in a new value in there. So it's essentially doing a swap. If you really want to think about it, it's doing a swap of two values in memory behind the scenes. And we can see that again if we also add, for example, simple map. Oops. Hold on a second. I hate when I use this. I'm going to use lookup collection key. Let's say y equal to 0. And if we go ahead and increment y, we'll get 1. And then let me actually do this. Width actually I think is the only thing that will not do what I'm about to do. So with simple map y, no, z3. I think I can do this. Yeah. All right. So now if we just go ahead and do the it would not actually go ahead and do that. It will actually go ahead and replace it with the default value. This is the one thing that you would have to understand. If you're using, actually I think before I didn't have C in there. With simple map. Yeah, that's right. It will create the new one. Yeah, I'm just confusing myself a little bit there. Okay, so with just there is a difference when you're using with and when you're doing a combination of incf and at or lookup when you're dealing with map structures. And assignment and updating in general when you're dealing with any of these data structures, and this is kind of what I was trying to get at, is should be treated the same as if you're essentially creating a new data structure with those new values. And when you're updating a data structure, you are essentially doing the same thing. Although some of those functions have setf style similarities, and their semantics are more in line with like incf and push when you're dealing with those kinds of data structures when you're looking at it from a vanilla common Lisp side. One specific topic that I want to bring up is generic functions that are available with FSet. I've kind of mentioned that internally FSet does have some sort of object hierarchy that's around it, and it has particular particular functions, generic functions that are associated with its internal structures are usually hidden in such a way that you can only really leverage them in particular situations. One of them is convert. So when you wanted to switch between different types, different FSet types inside of the library, like say if you have a bag and you want to convert it to a set, or if you're doing in similar conversions, you have to have a way of doing that. And with that, you have the convert API, which allows you to go from one type to another type. So some of the important conversions that you can do is use sets, maps, and bags and convert them to common Lisp types like lists and vectors. Additionally, you have two other interesting conversions, mainly sets to bags and sets to seeks. Maps to bags and maps to seeks aren't going to be very useful, so you're going to probably end up using that to make like an associative list and convert them to a list accordingly. You could see from the function signature that there's quite a few parameters that end up dealing with the collection and what the destination type is. Specifically, there are many different keyword types to specify different aspects of the actual conversion. One example of this is and we're going to look at this, is two ways of actually being able to convert a bag to a list. Okay, so if we recall, what is a bag doing? It has a compressed version of. Oops, I'm in the wrong. Let me change back to our other package. What am I doing? Just do this. There we go. FSet convert. So if we actually look at bag 1 and bag 2, if we remember what bags are, as we saw earlier, they are a compressed version of a particular list of values, all right? So there's two different ways that you can convert them. You can either convert that bag into the flat list with all the repeated elements, or like what it is here, you could create it into an associative list and have the list hold the multiplicity factor so it can maintain this representation. So one way of doing that is by using FSet convert, and then you specify the to type to list bag 1, and you can specify the from type as a list. If I remember correctly, this is how this is going to work. From type valid keys are. Did I mess that up? Yeah, I may have. Hold on. Okay. From type is not in there. No, it's there. Let's see what this is doing here. Invalid keyword argument from type for FSet convert. I could see it in the list, so I'm just surprised that it's saying that it's not to type is list. Let's see if I could do this and not have to specify a from type. So by default, if you're converting to a list, a bag, it will create the flattened list with repeated elements. But for some reason, it wouldn't allow me to provide the from type. So let's see what happens if I do this. There's no, that's right, there's no to type for an associative list. Target type list or a list. A list is not there. What is the way to do the a list? Again, I thought I can use a list based on what I was looking at earlier. Let's see if I can do this as a vector too as well. I doubt I can do that as a vector. Ah, nice. Let's see here. What is the A-list one? Function car, all other keys. So one of the reasons why A-list isn't working is A-list is not actually a common Lisp type, but FSet claims that it actually provides. Ah, that's what I need to do. I have to provide it as an exponent. There we go. So if you see this particular difference from the list and the A-list, and I apologize, A-list is not a common Lisp type, but I forgot that I'm not actually using FSet in my package. When you're converting to an A-list, an associative list with bag 1, it will create a set of cons pairs. And it's clear here that these are cons pairs. For folks who aren't familiar with the syntax, it is a dotted pair, where the car is the left side, the cutter is the right side. If you're not familiar at this point with this cons and dotted pair, I encourage you to go look at our introductory videos for Common Lisp to get more information on this. But this is particularly important to be aware of. You can also use this guy, and this time I'm just going to go ahead and do straight up. Use this, convert our stuff in between different sets. Now, you could take one of our sets, like our predefined set, which had a set of unique elements, and convert them to a bag and so forth. And of course, you can convert this guy into FSet seek to as well. The one thing that I will say is maps, because I mentioned maps earlier. Maps will actually work well with, let's go ahead and say vector here, sorry, list, typical, common Lisp list. And we can use that for example map. Example map. Populated map is what I wanted. Actually, I'll use another populated map. Another populated map. And what that does is it converts the populated map into an actual list of dotted pairs. This is the only situation where you can take this and convert it into an associated list, whereas one second. Okay. So where was I? Yeah. So this is, with maps, this is the only place where you're going to end up having to deal with associative lists directly as the conversion, versus what we were seeing earlier with bags. Because bags have this unique representation of holding this multiplicity factor there, and there's different ways that you want to convert them. But you can't actually, and I'm just going to show this to you because this should throw an error, convert, say, into a set, a populated map, because semantically there isn't any clear way of converting this from a map to a set. It's going to do some weirdness like this, which might look okay, but I don't know exactly what that what that represents. Additionally, you have the ability to convert this guy to, say, a sequence. But it's a sequence of dotted pairs. This is kind of what I'm trying to illustrate here. I'm basically saying that you're always dealing with, when you're dealing with maps and you're converting it into any of the other types, the types are always going to end up being a set of dotted pairs. It's not going to be a set of, or it's not going to do any sort of like magic behind the scenes to actually convert them into a pair that is structured inside of that set in some unique fashion. All right. And this is even the same if you're converting this into a bag, if I'm not mistaken. And there's not even a ability to actually convert a populated map into a bag. Okay, so that's something I didn't realize when I was going through it. But this illustrates my point, though. Some of the conversions make sense, some of the conversions don't make sense. So please, when you're playing around with this, know what you're trying to do, and then the appropriate conversions would become better for you. Let's talk about iteration here. Iteration is pretty much the same. You would use most of your common Lisp collections. Standard functions and standard use cases for iterating through most FSet collections is there is a philosophy behind iteration inside FSet, and that is usually you're only iterating to compute a value because you can't modify anything inside the collection. There's no point in doing anything other than analytical functions for dealing with these collection iterations and try to implement reductions of some various sorts. And the FSet library is no exception in that it has a plethora of APIs and function calls to make it easier to compute various values and iterate the particular sequence types that are available. So some of the stuff that we're going to be focusing on here is going to be mainly really dealing with sets and seeks. I will probably mention the iteration macros later on, but these functions that I'm going to be briefly mentioning here are going to be associated with iterations through those collection types themselves. The first thing is obviously, actually I'm going to go ahead and do this here, is dealing with essentially mapping something to something else. All right. Now, the first thing is that's going to be asked is well, why not just use mapcar to actually do this? Well, there's some specific situations where there are certain optimizations that are being done when you're using this particular function when you're mapping. So let me just first introduce the actual function itself. Image is the name of the function, and you can see that image has two different versions, image and image-f. Image-f is talking about places in the functions that you're dealing with, versus image, where you pass in a particular function in a collection. And for the cases of what we're talking about today, we're going to be dealing with just image right now. Image obviously does what we have before. It'll take in a function, and it will allow you to pass in a collection. So let's say if we have like a collection of 4 elements, and we want to increment each one of them. When you run this guy, and print out its results, you can see that it will automatically go through and iterate through those functions. You can similarly do what we do inside mapcar, which is if you pass in the actual 1+, instead of doing what a lambda is here, you can certainly do so. This is for also named symbols that are available for you. And it'll do the same thing. In this respect, you have some similarities with common Lisp's mapcar. And certainly, if you use mapcar, you think you will end up being able to actually use this. But if I remember correctly, because these are specific object types, this will not actually work. This will throw up an error. Specifically, sets are not actual sequence types. So you can't actually leverage the map car functionality in this case to actually go and do what you think it's doing. Additionally, image has some specific mathematical implications. It's trying to stay true to the actual definition itself. So the image is a set of another set. So an image of a set is another set that is mapped to the original values, and it could be a subset of the original set, or in some cases, its size could be smaller than the original set. An example of this is if we took this guy and instead of actually incrementing every element, we say lambda x if, let me do it this way, when even x, which will only, sorry, I'm just cleaning up this to make it a little bit easier to read what the function is actually doing. And what this is doing is it's going to take, one second, it's good, yeah. It's, wait, I must have messed something up here. Invalid arguments. Oops. Oh, yeah. Sorry about that. I forgot to pass in that. It's going to go ahead and it's going to dump out a set that is smaller than the actual set itself. What's interesting here is this set is 3 nodes. Oh, got it. I should actually do this. Other than that, do even x, if even x. Otherwise, return go ahead and do this instead, 1 plus x. Otherwise, we do that. Okay. What does this do? 1, 3, 5. Yeah. So what this is doing is in the first case, it's iterating through each one of them, and if it finds the first value, which is going to be 1, if it's even, it's going to just dump it and return it. Otherwise, it's going to go ahead and increment the value. It skips 3 because 3 is already inserted into the set, and obviously 4 is actually going to be incremented to 5 and so forth. You can see, though, that the size of the actual set is going to be smaller than the set itself. And this goes and talks about, the differences with mapcar. Mapcar tries to maintain the sequence type size, like the result sequence is going to be the same size as the original sequence itself. So that is one thing to be aware of when you're trying to map some of these FSet functions to what's available out there. Let's talk about filtering. So obviously we just saw map, and the next thing that if you want to do when you're mapping something is you may want to also filter some stuff off. For that we do have straight up the same thing, filter, to actually be able to filter a function. So let's do what we did before. Instead, use set with a collection of 4 elements, and we're filtering out all the evens. All right. This again has the same semantics. It could potentially be a smaller set than what is available. This can handle both sequence types and filters. Same thing here, actually. If we end up, using sequence here instead, you'll see that it'll become essentially a 1, 3, 3, 5 because of the fact that we're not actually removing duplicates. And finally, we have also reduce. Reduce is particularly useful when you're trying to, not just sum, which is, remember correctly, sum, I have to go in, plus is what I needed. If you wanted to, some elements, you'll end up being able to do that quickly. You'll also be able to deal with sets of sets here. So one nice thing about sets of sets is that we have reduce. With reduce, you can do union, take, set, and then pass in different sets. Here, FSet 34, FSet 4, 5, FSet 5, 6. And let's go ahead and add FSet here, 2, 3. All right, and if we do that, wait, did I mess that up? Oh, hold on a second. FSet union. You'll see that it will create 1, 2, 3, 4, 5, 6. This is nice for compressing some data sets. It's the same thing also if you use reduce when you're dealing sequence of sequences. I'm not going to illustrate that here, but you can clearly take these complicated data structures and then use these simple reduce mechanisms that we're all familiar with Lisp, deal with them with these appropriate FSet types. Now, maps are a particular interesting beast. And with FSet, they do provide some ways to iterate through maps and map structures. One way to deal with it is actually use their imperative iteration macros that they provide, which is very much all similar to their to using do list. If you ever use do list in Common Lisp, all the stuff that I showed you right now, there are equivalents for actually doing imperative iteration for sets, sequences, and bags. So one of them, and I'll just show you for illustrative purposes for bags, is do bag pairs. So you could do bag pairs, and we will say. So if you look at the function signature for do bag pairs, the first argument is going to be the value of it. The second value is going to be the multiplication factor, all right, how many times this value occurs. And then you provide, bag 1. And you could then iterate through this guy and just, say print x, print mult. And then actually probably easier just to do a format macro here. Sorry, a format say value a times occurring a, and then some bolt. And this guy will iterate through our bag and actually tell you how many times a particular thing is going, giving you a way to actually go and iteratively, well, imperatively write this code. Although I would recommend, if there's a way for you to write it in a functional way, to go and do that. For maps, you have obviously FSet do map, where you have the key, the value, and our good old map object. And you can do similarly t key value. Now, for those with the key and I, you will see in this case, this is very much like map hash. But you can't pass map hash. Just like all the FSet types are not available, are not equivalently lists or sequence types in Common Lisp. Maps are not types of are not hash table types, so you can't actually use it in that guise. But you have something similar. Wait, did I mess something? Oh, sorry. For some reason I decided to add that in there. There you go. Okay. So the last thing that I'm going to be iterating through, and then I'm gonna touch base on the final pieces in FSet in our final episode next week on this, is a particularly interesting macro that I've been trying to figure out the best ways to go and push this, but I'm sure others will look at this and say, there might be some particular use case for me, and that is gmap. FSet has a specific type of map macro called gmap. Why is gmap not showing up here? One second. It was available. Set prep package. FSet User. Maybe it's because gmap is available inside of FSet User, but it doesn't look like it's available inside. It's not exposed. So I don't encourage you to do this. This is the same thing for iSetQ if you really want to use it. But we're going to be talking about gmap here. I only mention it because I read about it in the documentation. I was like, oh, this looks pretty cool. And I used it in FSet User, but I didn't try it out in my main thing, so my apologies. But it is an unexported symbol, but it's a very interesting symbol that was documented. And what's particularly interesting about this, this function is the fact that it implements the author's opinion of the MapReduce paradigm. He's written it a number of years ago. The semantics are similar to how series kinds of works, but it's not as powerful. But it works with all the common use cases that are available inside. Inside our particular inside FSet itself. So the best way to illustrate this is with a simple example. What it does is the signature requires a specification, like a REST specification. All right. Say, for example, you're doing like a reduction operation. Okay. So you'd provide essentially what is your result. All right. you specify the function you're trying to do. Let's say that we're trying to do let's say so you need to provide a function that you're going to apply a map to. So like, let's say we're doing addition, okay? And you can provide particularly, let's say, some indexes associated with it, and you can provide essentially an argument specification to actually go in and to illustrate your sets that you're actually dealing with. So an example of this is, and this is something that's inside the documentation. Let's see if I can do plus instead of minus at times, as the documentation says. If we pass in our list that we're dealing with, let's say 1, 2, 3, right? And we map this, and we print it out, we end up seeing nine. Why is that 9? Hold on. Do I need to specify this? I could just do this. This is in its simplest form. If we do this, you'll end up using MapReduce essentially to grab each operation, all right, return the value, and then go ahead and run it, reduce it using summation. So the first argument is our reduction spec, okay? We're summing this guy. Our second argument is the map, is the function that we're going to use to reduce, all right? And our mapping is right now just a simple lambda that's going to return each value in the list, all right? This is what this list colon is doing. And what happens is since this list colon argument spec is basically saying that you're going to go ahead and use, it's going to use a simple lambda, grab each element, return it, and then summation it into a value that's going to be a single value. You can actually use the same GMap structure, all right, the GMap function to create lists, all right, or sets. So let's say that we're going to create a set, all right. We need to again specify how we're going to create this, all right. And we can specify multiple lists. Here we're actually specifying, let's say that we're going to create a set of values where the car is going to be an index and the cutter is going to be the particular like hash value of a particular thing, all right? So what you would do is you can create indexes here, and this is just going to give you an iota, an indexed sequence of 0, 1, and 2. And then we could specify additionally, a vector. And this is a common Lisp vector of arguments. And what this will do is this will create a key. One second. There we go. It'll create a set of the first car is going to be the 0 index, and then the cutter is going to be the value that we provided in the second list. So this is why this was 9 earlier. We were passing in an index of 0, 3 here, and 1, 2, and what it was doing is it was basically adding 0 plus 1. The map function was basically mapping 0 plus 1, all right? plus 1 plus 2 plus 2 plus 3, which is why this is going to be, this was going to be 9. So it ended up being 1 plus 3 plus 5, which is 9. So if we look at this, this is what this is doing. You can actually specify using this function, this map function, and it's all, and this is your reduce function, how to collect the results. All right. Are there questions about this? This is a particularly, this is kind of like the loop macro is the best thing I can come up with for folks who are looking at this and are like, man, this looks particularly familiar. It's very similar to how loop works. Its semantics turns out to be a generalization of mapcar, and internally, some of its semantics are bear a relation to series, which we've covered in past episodes. So it's a very nice little convenience API that you can use to actually do map reduce functions using the common FSet data structures. FSet does provide abilities to take all the basic types that it provide. It gives you sets, seeks, maps, and bags. And you can use each of those to has a type constructor into this function. So I just showed you sets here. I can also show you how maps could be used. So you can actually say, hey, I want to generate a map of the values of the index of 3 and the sequence of the FSet seek of these quoted items, right? And what this is doing is it's going to generate this kind of the same thing that we saw earlier with the set, but instead this is an actual basic map of key value pairs. All right. You can also use this to generate sequences and sets. I'm not going to show you seeks and bags right now, but I think this should give you some sort of intuition on how you could possibly use this. So that's it that I wanted to. I thought I'd be able to cover more, but it looks like we're running over here. I'm gonna stop right here and leave the floor for questions from folks, either in our live stream or folks that are on the Hangout. Other than that, next week our final piece on FSet is dealing with just another way of how to handle iterators and creating custom iterators. Mainly, there is a way of doing it using like get and next value, but I need to kind of really cover some of that stuff a little bit more in detail. That's a little bit more involved. There aren't many examples that I was able to run off of. I have to come up with some. Additionally, we'll be covering indexing and rank access, comparisons in FSet and equality, and some interesting functions that FSet uses to know about. And more importantly, and this is really, really useful for those of us who want to really heavily use FSet, how to create member types so you could set up your structure and class types for use inside FSet collections. That's something that should be particularly useful to talk about. So that's it. Are there questions? And I appreciate for those of you calling in and talking to us from France and other international locations. You guys are really ask questions away. If you guys have particular topics, let me know. Post them on the comments inside YouTube, and we will get to it. All right. Thanks, folks. I will see you guys next week. I appreciate you joining us today. Like I said, next week is our final coverage of. Hopefully, we'll be finishing up FSet, and we'll continue our exploration of data structure libraries in Common Lisp. See ya. Bye.